Welcome to Krishna's classroom. Let us continue with our exploration of compact sets. In this context, we introduce two new terminologies, namely total boundedness and epsilon net, which represent important properties of sets in metric spaces or metric spaces itself. Yes. Now, they are important, or these properties come up to highlight in the context of characterizing what are called compact sets. And our ultimate aim is to give a characterization of compact sets. So before we do that, let us explore these two concepts. Okay, so let me start with the definition of totally bounded set. A subset A of a metric space XD is said to be totally bounded epsilon positive. There exists a finite number of points set a finite number of points xi, I running from 1 to n, that means for n number of points, for some n, such that A is contained in union of I equal to 1 to n, B xi. What does it say? See, what it says is this. We say that A is totally bounded if there exists a set of finite number of points in X, not necessarily in A, such that B xi epsilon are epsilon neighborhoods of the point xi in the metric space A, and you see that A is contained in union 1 to n B xi epsilon. That is true. Then you say it is totally bounded. Now, this should be true for every epsilon positive. What does it mean? And this I would depend on would depend on epsilon. Natural. Okay. So what it says is that for any epsilon positive, there is a corresponding set of finite number of points in the metric space, which we designate by xi, such that the epsilon neighborhoods of these points provide A with a open cover. If that is the case, then you say it is totally bounded. Now we shall make a remark. Xi need not be that means those points can be from X. Now we define what is called epsilon. They are related. Suppose A is a subset A of X is called an epsilon net. An epsilon net if there exists finite cell which we designate by A such that or I think we'll put it this way. If distance of A for any x belonging to X, distance of X to A, which is equal to dA X, is less than epsilon. What does it mean? See, you have a subset A with the property that every element of X is at most at a distance of epsilon from it. Then you say A is an epsilon net. Okay. What is the meaning of that? This means that A, the property that for any x belonging to A, the ball with epsilon radius intersection A is so this is what it says that see you have A, this is your x. What it says is that suppose you have an x, then take an x. When x is inside A, the distance from x to A is already 0. So for x belonging to A, dAx is already equal to 0. So we are only concerned about the points outside. Now look at this statement. It says that suppose you take an epsilon neighborhood of x. What we assert is that its intersection with A is non-empty. So Bx epsilon intersection A is non-empty implies there exists an x prime belonging to A such that D x prime x prime less than epsilon. Okay. So this provides the A with in that case you say that A is an epsilon net for the whole of x. That means any point in A is within epsilon distance from any other element in x. Okay, so that is what you call an epsilon net. Now let us look at the consequences of these concepts. First of all, let us try to understand some interesting examples. Take R. Y equal to and A equal to some interval goes in. Then for any epsilon positive, there exists B Bx epsilon That means there exist points x1, x2, etc. xn. How do we prove this? First of all, you observe that AB is a compact subset of R. So consider the open cover x belonging to x. This provides A with a open cover. That is, A is contained in union x belonging to x. B. This is true for every epsilon. Okay, what is the consequence? The consequence is the following. Since AB is the closed bounded interval is compact. See that every open cover set finite set. Compact, we have seen earlier. There exists a finite subtype. Hence, there exists such that A is contained in E xi epsilon. Since this for every choice of epsilon, yes, the number also depends on now this is an example. So we will take the first example. Now let us take a second example. Take we know that Q is what is the consequence? The consequence is that given epsilon positive, there exists and for any x belonging to R, the distance of is less than. Therefore, or R, and all this contains some deeper general results which we shall explore later. But we are at the moment just working on some familiar situations. Now let us explore this further, and we will take up some nice examples or even general statements which are the consequences of this. Let us write down the results that you get. So one of the things that we observe is this. Okay. A metric space is totally bounded if and only there exists a finite epsilon net or as we have seen in the case here, Q becomes a epsilon net, but it is not a finite epsilon net. The reason being that R is not compact. But if a set is compact, then you are going to have what? How do you actually prove this? Okay. Go back to the definition of the total boundedness. Total boundedness, we have made this statement that given given x, if x is a totally bounded metric space, then there exists a finite set of points which is the property that for a given epsilon there exists a finite set of points such that the epsilon neighborhoods of these points form a open cover for the metric space X. Okay, so this is so total boundedness means that and a finite epsilon net also means the same thing. Okay. This is total boundedness. Finite set of points. Now these points would depend on epsilon. Such that, the important part is the finite set. Such that X is union epsilon. And that shows that this implies the collection x1 is now x, which is also finite. So conversely, suppose x1, x2, etc., xn is a finite epsilon, is an epsilon net for x, which is finite. Then, and assume that for each epsilon there exists a finite set of elements x1, x2, etc., xn, which is such that x is contained in this. Then what does it mean? It means that the x is totally bounded. Okay. Conversely, suppose for every epsilon there exists a finite x serving as an epsilon net for x. Okay. And this is for every epsilon. And you have a finite subset. This implies